If you have ever bitten into a perfectly fluffy pancake or chipped a tooth on a rock-hard biscuit, you have experienced the results of a mathematical equation. The difference between a light, airy breakfast and a dense puck of dough comes down to strict chemical ratios. Looking at this chart comparing mixture ratios, you can see how water and flour determine structural integrity. A pancake batter sits at a 1:2 ratio of liquid to flour, but if you increase that flour content until you hit a 3:8 ratio, you create a stiff dough, thickening the mixture until it supports its own weight. The math scales to other ingredients too. A higher fat-to-flour ratio coats the gluten proteins, preventing them from stretching. This specific proportion is exactly why some recipes yield a dense, chewy brownie, while others bake into a crumbly, cake-like dessert. Oil and water naturally repel each other. To create a stable mayonnaise, a chef relies on the amphiphilic properties of an egg yolk. The yolk contains molecules that grab onto both oil and water simultaneously, which binds them together into a smooth, stable emulsion. Without these precise measurements, the chemical structure fails. Baking is essentially the application of ratios to ensure our food holds its intended shape. The math that stabilizes our food also coordinates the invisible vibrations we interpret as music. This geometric frequency wave shows how Western music is organized into octaves. From one note to the next, the pitch frequency increases by exactly 5.95%. Compounding that increase across 12 notes, the final pitch vibrates at exactly double the starting frequency. Jazz legends like John Coltrane utilized these spatial tonal relationships to innovate. He drew geometric diagrams to map out how these mathematical connections could be used to bridge different musical keys. Whether measuring the density of a batter or the harmony of a saxophone, mathematics provides the universal framework for physical texture and auditory pitch. These calculations operate on a human scale, but when we look at planetary systems, the math must account for billions of moving variables at once. To predict where a storm system will travel, meteorologists rely on calculus. They use partial differential equations to process massive datasets on fluid dynamics and air pressure, modeling the motion of the atmosphere. The GPS in your phone operates on a similar scale. The network utilizes linear algebra to calculate the microscopic time delays in signals beaming down from orbiting satellites, pinpointing your exact location on the ground. Modern civilization depends on these advanced numerical models to impose predictable, reliable order onto the natural chaos of the world. But the highest stakes application of mathematics happens out of sight, within the digital layers that secure our private information. Encryption functions by scrambling readable plain text into ciphertext, a string of unreadable gibberish. Only the intended recipient can use the specific algorithm required to reverse the process and restore the data to its original form. This security relies on a concept called mathematical asymmetry. Most modern systems, like the RSA algorithm, are built on the unique behavior of prime numbers, such as 53 and 97. For a computer, the forward process is simple. You can multiply these two numbers together to reach a product of 5141 in a fraction of a second. But the reverse process is much harder. Forcing a computer to look at the number 5141 and deduce which two trimes were used to create it is computationally draining. When the numbers used are hundreds of digits long, the factoring process becomes practically impossible. Every secure text and online purchase relies on this specific bottleneck. Digital privacy functions because prime factorization requires too much time and energy for even the fastest traditional computers to crack. That digital armor is about to face a challenge it was never designed to stop. Scientists are currently developing quantum computers. Unlike standard processors, these machines can factor giant prime numbers in minutes, a task that would take today's most powerful servers several decades to solve. Once this technology is realized, current RSA encryption will fail. Global banking records, medical files, and private communications would be instantly accessible to anyone with a quantum processor. The mathematical difficulty that protects our digital infrastructure has a definitive expiration date. Mathematicians are already engineering a replacement security layer known as post-quantum cryptography. These algorithms use lattice cryptography. Instead of prime numbers, data hides within a multi-dimensional maze of intersecting vector lines. Even a quantum computer cannot solve these easily. The lines shatter the processing signal, creating a puzzle too complex to navigate. From the texture of our food and the harmony of our music, to the survival of the internet itself, mathematics remains the ultimate operating system of our reality.